Good morning, everybody. So we got a busy week this week, and a lot of material to cover. And this Friday, I'm going to hold in-person class. Okay, so the way this is going to work is I've created a sign-up sheet, and there's a link to it on the website on Sakai. Here, I'll show you. All right. Let me mute my other computer. Okay, so what I've done is I put some links here. Oh, look, there's a link to YouTube Live. And didn't work. Hold on. Oh, look at that. Goes right to the live stream. Link to WebAssign. Here it is. Recitation sign up. So I'm going to call these Friday sessions recitations. Recitation just means work with smaller groups on the course material, and this is going to be a little bit of a challenge, and the reason is there's a lot of material that we got to cover, and we have limited amount of time. So in order to have these recitation sessions, I think what I'm going to have to do is I'm going to have to also post, let's call them asynchronous lessons, for you guys to watch and learn from, to cover additional topics that we don't have time for during these live streams. Okay, but so the way this is going to work is these are optional, but I'd love to meet you guys in person, at least most of you, and so I've created this website that's again linked to here from the side panel in Sakai, and you can go, oh, look at that, a bunch of you already signed up for Friday. Okay, so let me just say this, that don't sign up more than a week in advance. I've created sign-ups for the entire semester, but I don't want you signing up until you know for sure that you're going to be able to come, because you know, if there's only 12 slots, I might change that. I got to recheck the room and see who else is using it, and there may be room for a few more people obeying the social distancing mandates, and so I might change that from 12 to 13, 14. We'll see. But as of right now, there's only 12 slots, so it's going to be sign up, first come, first serve, and this is so that people don't show up that aren't allowed to be in the room. Okay. So I hope that's clear enough. It's, you know, this is a learning experience for everybody, how to best manage this. So this is my plan as of right now. Starting this Friday, we'll meet in person, and we'll adapt if necessary. All right. Okay. On to physics. Okay. Well, last time, this is pretty much where we left off last time. And we had started with first principles of physics, the definition of average velocity and average acceleration. And there's a piece here that, well, here's the definition of average velocity. And the piece that's missing here is these are all derived, these expressions are derived under the assumption that acceleration is constant. And in that case, average acceleration, if acceleration is constant, average is equal to instantaneous, and that allows us to arrive at this equation right here. So what we did was I pointed you to material in the textbook which was showing how you could combine these expressions to get new expressions. These guys down here. All right, and so today I want to do some problem solving to see how you would apply these formulas. Let's call them your toolbox, your kinematic equations of motion, and they go into your physics formula toolbox to solve some word problems. So I'm going to open up WebAssign, and we're going to work on two of the problems. All right, we'll work on one of the problems, and then I have some new material to introduce you to, and then we'll work on another problem. And then we'll see how time is and maybe cover something too, something else additionally. All right, so if you have any questions, post them up in the comments. I got your comments here in front of me, and I'll try to answer them as best I can. I'll try not to miss them, all right? Okay. So let's go, close that, and go to WebAssign. I hope you guys have, if anybody has run into problems signing up for WebAssign, let me know. All right, it looks like I haven't done a exhaustive check, but it looks like at least the vast majority of you have been successful at signing up. Okay, let's open class view. So this is what you guys see when you log on. Oh, look at that. I changed the due date from Wednesday to Friday. Okay, so this homework is due Friday now. Okay, so the problem I want to look at here is let's look at this one, problem 10, and let me resize this. So, you know, one thing you guys will see in introductory physics is a lot of problems are structured in it's saying a particle moves, and you know, ask yourself, how often in your everyday life are you going to encounter situations where you're trying to study a particle? And the answer is never, unless you become a particle physicist. But remember that, you know, physics is concerned with creating mathematical models for the real world, whatever physical reality is, and the nature of the problems in the textbook are such where there's lots of simplifying assumptions that are made, and this is done to bring the scope into a domain that we can model using algebra, mainly algebra and calculus. And so that seriously limits the scope of problems, but it's not for nothing, because you know, one of the skills that physicists develop is the ability to kind of see the world like an onion. You know, any given situation is an onion, and you can peel layers away and focus in on the layers, the dimensions, the aspects which are most important to understanding the problem. And so that's a skill that you can cultivate. You know, you can focus on, you know, in any given situation, what is the most important thing. Anyway, I digress. So in this problem, there's a particle that moves in a straight line with an initial velocity of 25 meters per second and a constant acceleration of 34 meters per second squared. Oh, whoops, I didn't want to do that one, sorry. I want to do number 11. Oh, look at this. A particle has constant acceleration. Due to the nature of this problem, do not use rounded intermediate values of your calculations, including answers submitted to WebAssign. Okay, well that's a clue. It says don't round prematurely for your answers. But you have this particle that's accelerating at 6.8 meters per second squared. Notice that the units for acceleration, acceleration is a change of velocity. What's velocity? It's a rate, meters per second. So if you say how quickly is velocity changing, you have meters per second. So it's a rate of a rate. So that you get those units of meters per second squared. So these would be the SI units, the standard units for acceleration. You know so there's two parts, A and B. You know the initial velocity. At what time is this displacement 5.6 meters? All right, so let's go to the whiteboard and attack. All right. And so in this problem, it's good practice to develop a let's call it a problem-solving routine, a problem-solving strategy, problem-solving routine, a template of sorts, your default position, your default steps for when you attack a problem. And I'm going to prototype a good one for you. You'll develop your own, which will be some riff on this basic structure, okay? And it goes something like this. Step 1, read the problem, okay? Step 2, draw a picture. And in this case, this picture is pretty boring, but let's draw a particle and let's indicate that it's moving in a direction. And what we know for part A of this problem is the initial velocity. Let's use the symbol V0 for that. I ordered a new pen. It's supposed to get here tomorrow. It's not the $100 Microsoft pen. It's the $30 knockoff version. And the initial velocity is 1.5 meters per second. And we know the rate of acceleration is 6.8 meters per second squared. All right, so I drew a problem. I'm actually skipping to the next step, which is write down your knowns and your unknowns. And the things that we know, well, we could say, it's not given here, but we could say, well, at time 0, x0, its initial position is 0 meters. Things we don't know. We know, well, here's another thing we know. The problem says that its final position is 5.6 meters. It doesn't say that exactly. It says once it's done moving, its displacement is 5.6 meters. So it's sort of like, you know, x naught, the initial position, is understood. You say, well, let me say it starts at 0, and then when it's done moving, it's at 5.6 meters. That's its displacement. So its final position must be 5.6 meters if it started at 0. And what we're asked to find is t. How long does it take to go 5.6 meters? And, you know, we also don't know v, its final velocity. Okay, so I've kind of done this free form here, but one thing you can do it backwards here, but you could create 2 columns on your page and label one column known and the other column unknowns. And then summarize. So read the problem, draw a picture, write down what's known and isn't known. So, you know, one thing that I'm doing here is I'm assigning variable names to these physical quantities. So I'm mapping, I'm already mapping. I'm taking these physical things and I'm mapping them to the language of mathematics. Variables, okay? I'm projecting these physical things into the language of math, which is variables. There's a really important thing that I should add to my picture. So in the comments, I'm going to talk about it, and let's see if you can pick up on it. All right, there's a really important thing I should add to my picture. And this thing will clarify an important aspect of the vector quantities in this problem. All right, vectors have magnitude and direction. And in this case, we're simplifying the world and saying this is a one-dimensional motion. So it's motion in a straight line, along a straight line. But there's something I need to do. Does anybody know? Good morning, Tristan. Good morning, Steve, Chris, and Mike, and yeah, direction reference. Yes, Tyler, you got it. Okay. So the way I like to do this is just on my picture, draw an arrow, and label one direction positive and the other direction negative. And in this case, it makes sense to call the right positive, since that's the way I drew my picture. It's moving in that direction. Okay. All right. Read the problem, draw a picture, define positive and negative direction. Summarize knowns and unknowns. Step 4, look at your physics toolbox, your formulas, and find something that you can use to connect the knowns with the unknowns. All right. And then step 5 is solve. But this next step is the hardest part. Okay, so let's just take, in the physics toolbox that we have, one equation we have is, well, we have this formula. The average velocity equals sum of initial and final divided by 2. Is this going to be helpful in this case to connect knowns and unknowns? No. And the reason is because there's two things in here we don't know. So you can't use one equation to solve for two unknowns. What about this one? X equals, oh sorry, I'm getting ahead of myself. Let's do this one. V equals V naught plus A times T. Will this one be useful? And let's look and see. Well, we know what this is, so I'll circle in green what we know. We know this, but we don't know this, and we don't know this. So initially, that's not useful either. How about this? X equals your final position equals your initial position, x naught, plus your initial velocity times t, plus 1/2 a t squared. Okay, well, we know this, we know this, we know this, we know this, and the things we don't know are t's. So there's only one unknown in this formula, so this could work for us. But the problem here is that the unknown isn't here mathematically as a t squared. And so in the comments, if you have a formula like this, algebra like this, where the thing you don't know is squared, and actually you have two of these quantities in this formula. One is squared and one is to the first power. What tool do you have to use to solve for the unknown in this case? So if you know what it is, put it in the comments, but I'm going to go on because this you could do, but I put in a blue X here. It would work. It would be hard because of the algebra. What about, this equation? V squared plus V naught squared plus 2 times A x minus x naught. Okay, well, we know this, we know this, we know this, we know this. Bingo! We found a formula that has just one unknown, V. So we can solve for V. It's going to equal the square root of that. And so now it's just plug these values into your calculator and solve. And I got V equals 8.855 meters per second. Yeah, or Kara, am I saying your name right? Please tell me, Kara. I can't remember what you told me to call you. I can't remember. Sam or Kara, I'm sorry. You put some clarification in the comments. But you're absolutely right. It's the quadratic formula. So this bad boy up here, you could solve for t using the quadratic formula. But so what I'm doing here is I'm taking a path of least resistance, and I found one of my unknowns. And then once you find an unknown, so once you find something that's unknown, it's known. It becomes known. Okay? So now essentially V goes into that column over there. And now you're like, well, I still need to find T, but that becomes easy because now I can circle back around to this formula. Let's go over here and solve it for T. So just rearrange that formula, solve for T. And now I know all these things. And T equals Kara. Am I saying it right? Kara. 1.08 seconds. Okay. All right. So let's go back here, and you know, and this, it's fine. I actually found this right. I found this first, and that's part B. But there's nothing that says you can't find part B first. And so I'll put these in here and submit my answers, and let's hope I get them right. Yay! Yes. Okay, great. All right. All right, so let's summarize this one more time. So what we're doing is what you have to do. I can't do it for you. What you have to do is develop a problem-solving framework for physics. And what you wanted this framework to be is as general as possible so that any problem you encounter can fit into this framework. And a good way to think about it is steps. But you know, don't think of it as being overly rigid. You know, you can be flexible. The steps don't always have to happen in the same order. It's not like you go to step 3, you can't come back to step 2. All right, this is you know, you're creating pathways in your brain to think about physics. All right. So this framework that I laid down for you today goes something like this. You have a problem, you read it. You might have to read it many times. I drew a picture which included defining positive and negative direction. I summarized what I knew and I didn't know. And then I endeavored to use my physics toolbox, these formulas, these physics formulas, to connect what I know with what I don't know. And then I solved. So I could add another step here, and that step would be check your work. And in this case, WebAssign checked for me. But oftentimes there'll be, you know, red flags that will tell you that you did something wrong. You know, look at the magnitudes of the numbers you get. Look at the signs, positive or negative. Do they make sense physically? And then let me say one more thing. And this happened in this problem. You could have gone this route and solved for T. There's nothing wrong with that. So there's always, well, I won't say always, because there's always an exception to always. Most of the time, there's more than one way to solve a problem. And you know, that's another important lesson of physics. There's usually more than one way to look at a problem, and there's usually more than one way to proceed through a problem. All right. Okay, back to WebAssign here. And let's take a look at, I want to go down here, and one of the things, I wonder if this will work. I'm going to turn on my desktop audio. And one of the types of problems that I assigned to you are these things called video vignettes. And so I gave you one in the problem set. Put in my name. Click next.
Hi, Matt. What are you up to?
Hey, I was on my way to make a video for my students when I walked by and heard the music. What are you up to?
I'm working on some choreography. I'm planning on teaching this piece to my students this week. What's up with the video you're working on?
Well, the video is about motion with acceleration. You see, in cartoons, for example, characters that jump or get thrown in the air go up, stop, seem to think about it, then come back down. You know, in real life, how long do you think you'd have before you came back down?
Plenty of time. I can float. And you're not going to tell me physics says I can't.
No, I'm not. I think I'll talk to some people, maybe do an experiment, then I'll get back to you.
Okay, I'll talk to you later then.
We're making a video to help physics students understand motion. Now, just like a ball being tossed in the air, people can almost mimic this by jumping in the air. How long does a person remain at the top of their path when they jump in the air?
I'd say only a few seconds.
I'd say less than a second before they come back down.
Some people claim they can do this, specifically athletes, right? Basketball players, ballerinas, they all claim that they can do this. Are they telling the truth? Can they really jump in the air, seem to remain motionless and float and then come back down?
I think for an athlete, when they jump in the air, they may believe that they are floating for a second because of how high they jump, or there's other factors such as wind and resistance as such, but in reality, gravity is always going to take place once you hit your climax of where you've jumped, and you're going to go back down immediately.
Okay, so, excuse me, turn my mic back on here. All right, so in this video vignette, the topic here, it connects with the physics of falling objects, right? Falling objects. So if I drop an object, it falls and it accelerates, and the reason it accelerates is gravity. So the force of gravity pulls on objects, and if they're falling, that causes them to accelerate. All right. So there's foreshadowing here. It's the connection between force and acceleration. All right. Forces cause accelerations. All right. But right now we're just focused on the acceleration, and I can't really do this. Maybe I can. Let's see if I can. So I have a demonstration, and you need to see the grounds for me to be able to do this. Oop, that's the sky. There we go. Okay. So, got a marker, and let me find here a piece of paper. All right, so if I take these two objects and drop them at the same time, which one will hit the ground first? It's not even close. The marker. But now if I take the paper and crumble it up, all I've done is change the shape. Now, if I drop them at the same time, they hit the ground at exactly the same time. Okay, so the act of changing the paper, shape of the paper, drastically changed the way it fell. And so in the coming weeks, we'll study this phenomenon more. And the reason that this is happening is because of air drag. You change the shape of the paper, you change the way air drag affects the paper. It's a kind of friction. And so the motion of the paper is influenced by the motion of both objects is influenced by gravity, which pulls down, and air drag, which pushes up. And the total motion is a consequence of the total effect of those two forces. And what we saw was when the paper was flat, you couldn't ignore air drag. It had a significant effect. But when we crumbled it up, air drag became negligible. And in that case, the dominant force that governs how that thing falls is gravity, and air drag can be ignored. So here we're doing physics, and here's the layer of the onion that we're peeling off and throwing away. We're saying for certain kinds of motion, we can ignore friction, we can ignore air drag. And then we say, what happens if we just ignore that? We just focus on one force, in this case gravity. All right, so situations like this where we're doing this is called free fall. Free fall is a condition which doesn't exist on the Earth in the real world. Well, I shouldn't say that. You could create this condition in a vacuum chamber. There's a video, I'll post it on Sakai this week, there's a video that NASA does in this giant vacuum chamber to prove that if you suck all the air out of this giant vacuum chamber and drop a bowling ball and feathers at the same time, they accelerate downward at the same rate. It's really impressive. All right, so in the real world, everyday life on Earth, nothing is truly free fall. Even if you jump out of an airplane, initially air drag isn't very much, but eventually it becomes significant as you speed up. But many things, baseballs falling in the air, rocks falling down wells, even a skydiver, the instant he or she jumps out of an airplane, these are all things that are well approximated by free fall, assuming the only thing that matters is gravity. All right, so it's worth learning about this. All right, but one of the cool things about free fall is that all objects near the Earth's surface accelerate at the same rate, and that rate this is one of those constants that I'm not saying that you have to memorize it, but if you're doing things right, you're going to memorize it because you're going to use it so often. The acceleration due to gravity is 9.8 meters per second squared down. All right, let's write that down. Free fall acceleration is 9.8 meters per second squared downward, and this constant is so important that we give it its own symbol, g, for acceleration due to gravity. So g is 9.8 meters per second squared downward. And here I'm saying downward instead of positive or negative because positive or negative depends on your definition of those directions. All right, but downward is downward.
Let's do experiments to check this out. We'll use a video of a cart that's being pushed by wind from a hairdryer. Here's the video of it by the wind. Let's do experiments to check this out. We'll use a video of a cart that's being pushed by wind from a hairdryer. Here's the video of its direction being changed by the wind. How long does the cart stay in the same place while it changes direction? And what's the cart's acceleration while it changes direction?
So, turn this off. I don't know. This is pretty cumbersome switching back and forth between my mics. But in this video, they're saying, well, here's a horizontal situation that's like the vertical situation of someone jumping up and coming back down. And there's this perception that the cart comes to rest and stays there for a moment. And I think I'll let you work through the rest of this video on your own, but the main message that this is trying to communicate is that you know, the old adage, what goes up must come down. What's actually happening is on the way up, the object is slowing down, and then on the way down it's speeding up, and the reason is because of acceleration. Acceleration is always pointing downward, and you will get a little bit of more exposure to this idea in lab this week, but at that moment where it looks like the thing has stopped, come to rest, it has come to rest, but it's instantaneously come to rest for a moment in time that is, it's most accurate to say, no time at all. It's an infinitesimally small amount of time that it comes to rest. So a better way to think about it is that you throw a ball up in the air. When it reaches throw a ball up in the air, when it reaches its top of its path, it's in the process of changing direction. That's a better way to think about it. It's in the process of changing direction. It was going up, and now it's coming back down. All right, so let's work through a problem that involves this concept of free fall that I assigned for you, and we got 15 minutes. I think we'll get through it. Okay, here it is, problem 14. Okay, so in this is a problem that involves a diver on a diving board. So the diver jumps off the diving board, goes straight up, and comes straight down. Now there must be some degree of horizontal motion, but we're going to ignore that. We're going to say there's not much, and essentially the diver goes straight up, comes straight back down into the pool. All right, so a path that goes up, reaches the highest point, and comes back down. All right, and the question here says a diver bounces straight up off a diving board, avoids the diving board on the way down, and falls feet first into a pool. She starts with an initial velocity of 5 meters per second, and her takeoff point is 1.3 meters above the pool. What is the highest position point above the board in meters? How long in time are her feet in the air? And what is her velocity when her feet hit the water? And here it says, assume the positive direction is upward, indicate the direction with the sign of your answer. So we're being clued in that for vector quantities for this problem, so that you get graded correctly, up is positive, down is negative. Okay, so I've read the problem. Now let's go to the whiteboard and don't want to zoom out that much. And now I'll draw a picture. So I have here, there's a little bit more substance to my picture. I can even get a little bit creative. So there's my diving board, and there's my diver on the board. So she's going to go up and come back down, and I drew it a little bit with a little bit of horizontal displacement, but we're ignoring that for now. So the red line is the path she travels. The problem says let's call up positive and down negative. And now let's think about what we know and don't know. Well, we know at this point right here, where she starts, her initial velocity is 5 meters per second up. And the initial position, here I'm going to use y's instead of x's, because we're talking about up and down, is 1.3 meters above the water. And we know something about down here at the water, the y position there would be 0 meters. The things we don't know are how long it takes to get there, how fast is she going when she gets there, and then there's something else we know. Do you know it? So here we're going to strip away the layers of the onion and call this free fall. So there's something else that we know that I haven't written down here yet. What is it? Anybody know? While you're thinking about that and typing in the comments, I'm going to give you guys, good William, acceleration. You got it. And Holly, good. I'm going to give you guys another point in this motion to think about. And because we're asked about something like that, we want to know something about the top of her path. And let's call that, if this is point 0, let's call that point 1, and then down here is just final with no subscripts. And what do we know about that moment in time? That moment in time when the diver reaches her highest point. What do we know about that point? Just the process of changing direction. So she's momentarily, infinitesimally, for an infinitesimally small interval of time. What do we know? That is when the acceleration hits 0. Not quite. Quite. That is when velocity is 0. Correct. Okay. Not acceleration. Velocity. So I can, this is going to take a little bit of time to integrate into your brain. Acceleration is change in velocity. So think about it like this. If you go up to the top, if you jump off a diving board and go up to your highest point, and for a moment your velocity is 0, if your acceleration is also 0, what's going to happen? You're just going to stay there forever. You're stuck. If your velocity is 0 and it's not changing, because acceleration is also 0, it's going to be 0 and 0, and you're just going to stay there. And that's not what happens in the real world. Another way to think about this is free fall is governed by gravity. Gravity doesn't turn off when you're at the top. Gravity is always turned on. So that acceleration is always there. It's always 9.8 meters per second squared. It's always pointed downward. It's always on. Okay. So what we know is that at the top here, V1, velocity is going to be 0. And so what this means is we can break this problem, I wanted red, break this problem, I want fat red, here we go, into 2 parts. The part on the way up and the part on the way down. And record this. For all these portions of motion, acceleration is negative 9.8 meters per second squared. Okay, so let's do it this way. Let's say that let's look at the interval of time that goes until she reaches the top of her motion. And let's write down what's known and unknown. Well, we know the initial velocity during that interval is 5 meters per second. The initial position, 1.3 meters. The acceleration is negative 9.8 meters per second squared. And we know that when she gets to the top, we'll call that V1, for a moment, her velocity is 0. What's unknown? We don't know how long that takes, and we don't know how high she goes. Okay. So what we're doing here is we've created a problem that is just part of the situation, just the part where she's on the way up. All right, so broke it into the smaller part. It's a little smaller, needs more space. Okay, and then let's find an equation that connects knowns with unknowns. Well, let's just write some stuff down. How about, y1 equals, and so here I'm writing y's instead of x's, and the y has a subscript 1 because that's the moment in time at the top, equals initial position plus initial velocity plus 1/2 acceleration times t squared. Let's look at this. What don't we know here? We don't know this. I forgot the subscripts on the time. And we don't know time. So this isn't going to be helpful. There's too many unknowns right now. Well, let's look at a different equation. How about this one? The velocity at the top equals the velocity initially plus the rate of acceleration times time. Well, the only thing we don't know here is time, so yay. Let's solve for t. And so that's going to give me v1 is 0, so that's going to go away. A is g, which is negative 9.8. v0 is 5, so I end up getting, it takes her about half a second to get to the top. And now there's an interesting thing that happens, she's blue, that now that I know this, I can revisit that first equation because now I know t and I can solve for y1. How high did she go? And that turns out to be 2.576 meters. Okay. So I've solved the problem of how high does she go. And it turns out all I needed to know is how fast she was going initially. And I could figure out how high she went. Relative to the diving board. Okay, so now let's look at the whole thing. Because now maybe we can do that. So I could look at just the falling part. So I could take a look and say, well, let's look at top to bottom. But instead of doing that, here I'm just going to do start to bottom. Okay, and it's going to have to get smaller. And so here, go away. Knowns, so treat it as a new problem. Knowns and unknowns. And at the start, what do I know? I know V0, I'm just going to write down what I know. I know my initial position. I know my acceleration. I also know my final position. It would be y equals 0 when I hit the water. What don't I know? How fast I'm going when I get there, and how long it takes to get there. So the V0s, the variables that have the naught, the 0 subscript, is the initial when she leaves the diving board, and the variables that don't have a subscript are final. I could put an F there or a 2, but simplicity. Just not put anything. And so now, what can I use to connect my knowns with unknowns? Let's look at this one. V squared. This is in our toolbox, our box O physics tricks. Whoops. We know final velocity equals squared equals initial velocity squared plus 2 times a times change in position, which in this case I'll use y's instead of x's. So I can solve for V. And here I get V equals 7.105 meters per second. Okay? Because in this problem, it's the only term we don't know. We know how fast she's going when she leaves the board. We know her rate of acceleration. We know where she started and where she ended in the y direction. Okay, so I found that. So now there's a little bit of a problem here, and it's because of the mathematics of squaring something. When you square something, you lose some information. And it's because the math of squaring something is, if you have a positive number and square it, you get a positive number. If you have a negative number and square it, you get a positive number. So this equation destroys knowledge of direction. Okay? It destroys the knowledge of which direction you're going because it eliminates the positive or negative symbol from knowledge. But we have context. You know, the context is she starts going up and then she comes back down. So we said up's positive, down's negative. That means this must be negative. The instant she hits the water, she's traveling downward. That's negative 7.10. All right, we're almost done. I know, I'm out of time here. And t, we can solve. Man, time flies when you're having fun. V equals, so here's an equation of motion. V equals V naught plus AT. Solve for t. V minus V naught over A. And that equals 1.235 seconds. Okay, so we have everything we need to know to answer the question of WebAssign. But be careful. Read what they want you to ask, what they want you to put in there. So if we could look at the numbers here, what's her highest point above the board? So we figured out her highest point is 2.516 meters, but that's above the water. So you have to subtract her starting position at 1.28 meters. How long was she in the air? 1.24 seconds. What was her velocity? Minus 7.1 meters per second. Submit it and see if we get that right. If I did the math right in my head, yay. Okay, so again, the reason this is 1.28 instead of 2.52 is 2.52 is relative to the pool, but the answer is relative to the board. So we got to subtract 1.3 meters. All right, so I went a little over today, but I apologize for that. But I will see you guys on Wednesday, well actually tomorrow, so at 1:50 tomorrow afternoon, we'll get together via Zoom, all right, not live stream, but via Zoom, and discuss the lab for this week. And it's open now. You can get started on it if you want, and then I'll see you guys on Wednesday. All right, have a nice day.